Acids and Bases, Part 3, Bases. This video will help you to apply the Arrhenius and Bronsted-Lowry models to bases. You'll learn how to calculate the pH of an alkaline solution, whether it be a strong base or a weak base. Bases are substances that produce hydroxide ions when dissolved in aqueous solution. This is the Arrhenius definition. Remember that a Bronsted-Lowry definition states that bases are substances that accept protons in chemical reactions. Metallic hydroxides of group 1 and 2 are strong bases, so they will completely dissociate in solution. It should be noted that some group 2 hydroxides, like magnesium hydroxide, are not completely soluble, but they are still strong bases because every part that does dissolve completely dissociates. Magnesium hydroxide and other bases like aluminum hydroxide and calcium carbonate are often used as antacids for upset stomach. Calcium carbonate is also used in scrubbers to remove pollutants from the smokestacks of power plants and factories. So how would you calculate the pH of this strong base solution? 5.0 times 10 to the negative second molar sodium hydroxide. First of all, which species are actually present in the solution? Since sodium hydroxide, a group 1 hydroxide, is a strong base, it will completely dissociate, so it will form sodium and hydroxide ions in solution. As a result, the molarity of the hydroxide ions will be 5.0 times 10 to the negative second. Using the ion product constant from the autoionization of water, we can calculate the hydrogen ion concentration. The H+ concentration turns out to be 2.0 times 10 to the negative 13th molar. pH is the negative log of the hydrogen ion concentration, so in this case, the negative log of 2.0 times 10 to the negative 13th gives us a pH for this sodium hydroxide solution of 12.70. Perhaps we should note that the pH could have also been found just as easily by using the pOH of the solution. Since pH plus pOH equals 14.00, the pH is 14.00 minus the negative log of the hydroxide concentration. So 14 minus 1.30 also gives us 12.70 for the pH of this basic solution. What about a weak base? Many proton-accepting Bronsted-Lowry bases do not contain any hydroxide ions, so they increase hydroxide ion concentration in solution by removing protons from the water molecules. Similar to the acid dissociation constant we used for weak acids, you can write this Bronsted-Lowry reaction for the hydrolysis of a base, that is, the reaction of a base with water to produce its conjugate acid and the hydroxide ion. This reaction has an equilibrium expression of Kb equal to the conjugate acid concentration, BH+, times the hydroxide ion concentration, divided by the base concentration at equilibrium, B. This constant Kb only applies to this type of reaction between a base and water. It cannot be used with simple dissociation of metal hydroxide to form metal ion and hydroxide ions. Always keep this in mind when doing weak base calculations involving Kb. Here's an example of the reaction between a weak base, ammonia, and water. The proton is accepted by the base from the water molecule to produce the ammonium ion and the hydroxide ion. The Kb for this reaction is 1.8 times 10 to the negative 5th power. Just as with Ka values of weak acids, the lower the value of Kb, the lower the ion concentrations would be, so the weaker the base would be. Bases like methylamine, ethylamine, aniline, and pyridine all react similarly with water by accepting protons to form their conjugate acids and hydroxide ions. So let's close by calculating the pH of this weak basic solution, a 15.0 molar ammonia solution. Typically, calculations for the pH of weak bases are very similar to those for weak acids, just with a different kind of reaction equilibrium and a different kind of equilibrium constant. We'll start, of course, by considering which species are going to be present in the solution. Water and the weak base molecule ammonia will be our major species. The ammonia molecule will react with water to form ammonium and hydroxide in this green equilibrium reaction. We can set up an ice table to organize our initial concentrations, our change in concentrations, and our equilibrium concentrations for this reaction. Since water is a pure liquid in this heterogeneous equilibrium, its concentration will not be changing during the reaction and is irrelevant for our calculations. When the reaction reaches equilibrium, these green equilibrium concentrations will be our concentrations. The autoionization of water is an insignificant producer of hydroxide in this very concentrated ammonia solution. So we can use the equilibrium expression for Kb, substitute our equilibrium concentrations in terms of x. Since the equilibrium constant is so low compared to our initial ammonia concentration, we can use the 5% rule to approximate and save a lot of time. The hydroxide ion concentration would then be 0.016 molar, which is much less than 5% of the initial ammonia concentration. If we find the pOH and subtract that from 14, we get the pH of this solution. The pH is 12.20. Thank you for watching this video in which you learned how to calculate the pH for strong and weak base solutions. If you have questions, please leave a comment. Review your textbook or re-watch this video if you have trouble with this type of calculation. Next time we'll look at polyprotic acids, their pHs, and their equilibria.